So our next speaker is one of our guest keynotes, Nati Srebro from TTI Chicago. Nati's done a lot of great, interesting work on, well, generally in machine learning, but more recently on understanding deep learning and generalization. And he'll tell us about optimization's hidden gift to learning, and I'll let Nati say what that is. Thank you, Nati.
Hey. Thank you. So what I'll talk about today is maybe background to the talk you just heard from the Dove, which is about how some of our work we did about how understanding optimization is crucial in order to understand deep learning. And the starting point from this is a plot with which I start many of my talks. This experiment we did about 5 years ago, and I think the first time I actually presented it was also at an event here in Tel Aviv University organized by Intel. And at the time we were looking at this and quite puzzled by what's going on, and that's how I presented at the time. And now 5 years later, I think we have a lot more understanding. So what is the experiment we did at the time? And this was in order to the reason we did this was in order to understand the success of various optimization methods, was we looked at what happens when you train larger and larger networks without any regularization or anything, just minimize the training error. And so what happens when on the x-axis is the size of the network, and I should say if for each size it's trained completely independently, then as the network is bigger, the training error decreases. Sure, I mean, kind of expect that. And the test error also tracks it and decreases, and we can get a better fit. But the real question is what happens when we already have a network that's very large, perfectly able to fit the training data. What happens if we lose larger and larger networks? So what our sort of classical theory would tell us is at this point we're going to overfit. We're going to start having a deterioration of the test error. In particular, if you look at a network with 1,000 units here, it already has more parameters, many more parameters and training points, and there's no reason we should generalize at all. We should completely overfit. But what we actually observe in practice, and this is we observe in many different situations, and since then many others have also observed it, is that the test error actually decreases. So what's going on here? There are two things that are very strange here. One is, what's causing the test error to decrease here? It's not that we're getting a better fit for the data, because we're already fitting the training data perfectly. So it seems that we're getting better sort of complexity control or capacity control, but where is that coming from? But even if we don't look at the trend, what happens, why at all are we getting any type of generalization when we have many, many more training points and the amount of data? So if you look at the specific case here of 1,000 units, we're finding a network that actually has very good, that generalizes pretty well, that has pretty good error in the population, pretty good test error. But if the problem we solved is just minimize the training error on the data, and there are many other ways of getting global optima for that problem. So if I just told you, okay, you're optimizers, put on my optimization hat, and I say, just minimize the training error of this network, then you could have found me many other global minima. Each of these red points that I plot here, all of them are global minima of the objective. All of them completely minimize the training error. But as you see on the y-axis, most of them do not generalize well at all. They give pretty much trivial test errors. So why is it that we're getting generalization here at all? And so one explanation here is that what's going on here is that the real capacity control, the real complexity measure is not the size of the network, not the number of units, but rather some other notion of some weight of the network, some norm, something like that. And indeed, if I put here on my x-axis the norm, I put some specific norm, the path norm. It turns out if I put just a Frobenius norm, I would not get such nice results. I do in fact get a correlation between networks that have small norm and those that generalize well. But the first question we should ask is, what is this complexity measure? Why this path norm? And the answer is actually not the path norm. We definitely know that. We don't know what the correct complexity measure, but what is it that really is controlling generalization? But the second thing we should ask is, why at all are we finding these solutions with small norm? Why is it that when I ran gradient descent, I actually found this parameters on the bottom left-hand corner there that have small norm and also generalize well? I didn't tell this to my optimization algorithm. All I told it is minimize the training error, and all of these points satisfy that. All of them minimize the training error. So it seems that whatever hidden complexity is going on here is somehow implicitly controlled by the optimization algorithm, even though it's not hard-coded into it. In particular, that means that if I change the optimization algorithm, I'm going to change this control, and I might get different generalization properties. In fact, we can see that if we train the exact same network with the exact same objective, no regularization, using two different optimization algorithms, we get different results. So what we're showing here is two different optimization algorithms. One is SGD, the other is path SGD, which is inspired by this path norm. It doesn't matter. There's a blue algorithm and the red algorithm. On the left side, we see their training error, and both of them are finding global optima of the training objective. So both of them are doing exactly what they're told, which is optimize the objective. Maybe the blue out one is a bit faster. I don't really care about that. What I do care about is the rightmost plot, in which we see the test performance, and we see that the blue algorithm is finding a much better global optima. So what does it mean, a better global optima? I mean, they're both finding global optima. I know it's a global optima because it's zero training error. You cannot be better than that, okay? But somehow, the blue one is finding a better optima, and it's better in some, I'm being completely unfair here to the optimization algorithm because I didn't tell the red optimization algorithm to find something with small norm or find something that's generalized well. All I told them is minimize the training error, which it's doing. So it's better in some implicit way that I did not hard code. And we see that also with that regularization. Another example is if we compare again two optimization algorithms, this time SGD and ADAM, which is an adaptive variant of SGD with momentum, very popular. And again, both of these algorithms minimize, they're both going to minimize the training error. That's fine. In fact, here we see that the red algorithm, which is ADAM, is an optimization algorithm. It's doing actually a bit better. You know, it's actually minimizing faster. So, but now when we ask what minima they converge to, what global minima they converge to, we see that actually the blue algorithm, plain SGD, is converging to better global minima. And again, better in a way that's completely unfair to the algorithm, better in terms of some hidden thing that's going on here. So it has a better, it's bringing in some better inductive bias somehow. Okay? So what's going on here? I mean, we can say that what we're seeing is that because the network is over-parameterized, there are many more parameters, we need some additional complexity control, and it's coming in from optimization algorithm. So the optimization algorithm is biasing us towards particular global minima, and those global minima have induced good performance guarantees. So this suggests that we should study optimization algorithms, not just in terms of, oh, they're finding the global minima, but we should also ask which global minima are they getting to. So in this example, for example, if I start in the top there, this shows two optimization algorithms, in this case, gradient descent and coordinate descent. They're finding different global minima. And this is sort of, you can think of it intuitively as related to the geometry of the optimization algorithm. So all our optimization algorithms are essentially local search methods, and they do local search, though, under some geometry. So for example, gradient descent, roughly speaking, does local search relative to Euclidean geometry, and coordinate descent, roughly speaking, does local search with respect to some L1 geometry. And what the global minima they're going to find is a global minima that's close to them. Now let's go back to the energy to the loss landscape. We're talking about very over-parameterized networks. So there are many global minima. Okay? So you can think of these as the sea, as the oceans, right? There are many solutions that are at zero level, at sea level. We're going to start optimizing not at a solution that has zero error, but a solution that has positive error, so on some hill, and we're going to go down. And the question is, which global minima are you going to get to? So we're not going to get to a global minima in the middle of the ocean. We're going to get to some beach. And the question is, which beach? So if I start optimizing here, and I use pretty much any optimization algorithm, we know which beach I'm going to get to. I'm going to get to the Mediterranean pretty close to here. Okay? But the question is, what happens if we start optimizing in a more interesting place? Like, what happens if we start optimizing in Jerusalem? So now it's not entirely clear where I'm going to get to. If my optimization algorithm prefers going west, I'm going to get to the Mediterranean. If my optimization algorithm prefers going east, I'm going to get to the Dead Sea. If my optimization algorithm prefers going kind of south, I might even make it to the Red Sea. Okay? And so the optimization, so what I'm going to get roughly is a beach that's closest under the geometry of the optimization algorithm. And that's what's, I would claim, determines the generalization properties. Now, and that means that if we look at different learning methods, we tend to think of them mostly in terms of defining a model class, right? So we define some great new deep learning method. We talk a lot about how it's really it's a great model class because the model captures all kinds of interesting things. And then how do we fit it? Well, we just minimize the training error. How do we minimize the training error? I mean, the details are, in the appendix, or maybe not even the appendix, in the source code, maybe not even the source code that I can find. I don't really know, it doesn't matter. And what I'm saying, it does matter, because all the inductive bias is determined exactly by this optimization procedure. Okay? In fact, I'd argue that our models are so big that they can capture essentially any function. Okay? And I know that because we know we can fit, even junk labels using our models. So really, the model class is not important at all. The model class is the class of all functions. We're searching over the class of all functions, so we are not getting any type of inductive bias, any types of actual modeling through the model class. All the inductive bias of the learning, everything that drives generalization is just through the optimizational algorithm, and just through the optimizational algorithm prefers certain global minima to others. Okay? So this is sort of our view now, and what we're trying to understand is understanding this, what is the actual real inductive bias in deep learning, and how is it controlled by optimization algorithm. So if all this seemed a bit abstract, then we can see it in a specific example, and this is an example also that Nadav already alluded to. And this example is maybe the one thing that I understand fairly well, which is matrix completion. So let's think of a matrix completion problem and try it again. Our goal is to understand this phenomena of how we can search over all functions, but just by virtue of optimization algorithm, actually find interesting solutions. So in matrix completion, what's the problem in matrix completion? I observe some of the entries of a matrix, and I want to complete the unobserved entries. So you can think of this as, if you want, as a matrix of movie ratings for different users. So we have the movies on the rows and the users on the columns, or something like that. But basically, you have some partial observations, so you want to complete it. So I'm going to solve that. Well, I want to find a matrix. I'm going to find a matrix that fits the observation. So I'm going to optimize over the set of all possible matrices, searching for one that minimizes the error on the observed entries. Okay, does this make sense? Does it make sense? Yes? No? No? People are too big audience. So, this doesn't make any sense at all. This is completely stupid, right? Because there are many global minima here. Because all I need to get to global minima is to get zero error. All I need to do is make sure that X actually agrees with the observed entries. So I can copy the observed entries and then put zero everywhere else. This would be a global minima of this optimization problem. And of course, that's not going to help me at all in complete the unobserved entries. There are many other global minima. You can also, copy the observed entries and write the sequence of prime numbers in the unobserved entries, or just put 72 everywhere else. Okay? So there are many, many global minima here, and just minimizing the subjective doesn't give me anything. So this is a completely senseless optimization problem in terms of learning. And what we're going to do is exactly we're going to do what we do in deep learning. So we have a problem. The problem with this problem is it has too many parameters. Okay? And what we're going to do is take the deep learning approach, which means we're going to replace this problem with a problem which has even more parameters and is non-convex. Okay? At least the original problem was convex. Okay? So what we're going to do is we're going to write x as u times v. Okay? And u times v here are the same size as x. So we didn't impose any constraints in the model, because any matrix x I can write as u times v. Like, for example, I can write it as x times the identity. Okay, so my model class here is still the class of all matrices. And I'm going to optimize over u and v. So this optimization problem is just as stupid as the optimization problem I had before. I can complete the observed entries and write the Fibonacci sequence everywhere else. Right? Or complete the observed entries and put zero everywhere else. For example, by having u the matrix that completes the observed entries and has zero everywhere else, and v the identity. And there are many, many other ways. This doesn't make any sense at all. Okay? But that's fine. We're going to go with this problem that doesn't make any sense at all, and we're going to optimize it with gradient descent over u and v, just like we do in deep learning. And let's see what happens. And what we're actually going to look at is we're going to look at two things. What happens if I look at essentially two different optimization algorithms for the same problem. One is gradient descent over x, and the other is gradient descent over u and v. And this is what we get here. So first of all, we observe the training errors are fine. Both optimization algorithms succeeded in finding a global minima with zero training error. That's not so surprising, because this is a really easy optimization problem. The more interesting thing is the test error. The error in the unobserved entries are actually, the way it's measured here is the error over all the entries, both observed and unobserved. So if I optimize over the metrics here of them, okay, sorry, here it's called x, the metrics w itself. This is really bad for generalization. I'm not going to get anywhere. The test error is going to be trivial. But surprisingly, if I optimize this completely stupid optimization problem by gradient descent over u and v, I actually get pretty good test error. Definitely much, much, much better than random. So something is going on here. Okay? Now let's see what happens when I change my optimization algorithm, the same way I did before, like from SGD to Adam or something like that. So in particular, what we did here, the second from left plot is gradient descent with exact line search. And what I did instead is looked at gradient descent with a small fixed step size. So in terms of optimization, that's actually a worse optimization algorithm. It'll take it much longer to converge. The exact line search is a very good thing to do here. So the rightmost plot you see here now, which is red, I don't know if you can see that, is actually the worst in terms of optimization, but it actually improves the generalization even better. So already before I got good generalization, now I'm even getting better generalization. So can we understand what's going on here? Why are we getting good generalization? And at least in this case, we can sort of understand what's going on. And as Nadav alluded to, we still have, we don't have a complete and convincing explanation, completely rigorous explanation. But it seems that what's going on here is that by doing gradient descent and the factorization, we're at least approximately minimizing the nuclear norm. Okay? So we're finding not just any solution, we're finding a solution with small nuclear norm. So when we talked about before the distance to our closest beach, right? So the oceans here are all the matrices that agree with the training data. Okay? There are many such matrices. And I measure the distance to the closest solution by having small nuclear norm. So I'm going to start very close to 0, and I'm going to find a solution that's closest to 0 in terms of nuclear norm, so the minimum nuclear norm solution. So this is what the optimization does. Okay? And then we already have a theory that tells us that actually minimizing nuclear norm in this case is actually very good inductive bias. It leads to good generalization. Okay? And I should say that I would still hold that this is, I think we have a lot of evidence that this is at least approximately what's going on here. Nadav is sitting there and smiling. We can talk about it later. I'm sorry? Yeah. So there's a continuing argument, there's some others involved. It's definitely clear that something is going on here related to the nuclear norm. Okay, so what did we do in this case? So note that, as I said, we optimized over the space of all matrices, but we used a particular parameterization of it. And the key here was two things. When we talked about before about the geometry of the optimization algorithm, like coordinate descent versus gradient descent, then the picture is actually a bit more complex. Because we did have, it was important what geometry used in parameter space, but that induced some kind of bias in parameter space, but even more important was the connection between parameter space and the predictor space. In this case, the predictor space is a space of matrices. Okay? And this factorization induces a very, some kind of parameterization, and it translates every prior in, or every bias in predictor space to some bias in the metric space. And what we saw here is by having a relatively easy geometry, very simple geometry in parameter space, we actually got a very rich inductive bias, namely nuclear norm, in the predictor space, in the space of matrices. And we can see this in many other cases, and what I'm going to show you now is several cases where, again, we're optimizing over, in some sense, the space of all predictors, all functions, and just by choosing a particular parameterization, we're getting a very rich inductive bias. So the first example is an example we already saw. So in this case, when we say the space of all functions or the space of all predictors, the space of all matrices, right? We're not constraining the space at all. We're just choosing a particular parameterization, and this gives rise to the nuclear norm inductive bias. Another example which we studied is linear convolutional networks. So this is like your familiar convnets for simplicity with the full width cyclic convolutions. But the important thing here is the activations are just linear. So these are convolutional networks with linear activations. So these are, again, very stupid networks because if you use a linear convolutional network with linear activations, at the end of the day, what you're getting is a linear predictor. So the space of functions you're searching for here, space of predictors, is just a space of linear predictors. So it's just a very, very, very strange way to over-parameterize linear predictors. So what you're doing is just kind of like linear regression, or in this case, logistic regression. But you're optimizing your logistic regression using a very peculiar parameterization. And we're doing gradient descent over the weights of this network. Which linear predictor? I'm going to get a linear predictor. I'm going to get a linear predictor that actually separates the data, because I'm assuming I'm over-parameterized here, so I can separate the data. There are many ways of separating the data. Which linear predictor am I going to get? And so and just tell you that if I don't use a linear convolutional network, if I optimize the parameters directly, or if I use a fully connected network, I get the max margin respect to just the norm of the predictor. But if I use a linear convolutional network, it turns out that what I get is it's equivalent to minimizing the sparsity inducing penalty in the Fourier domain, so in the frequency domain. Okay? So I get sparsity in the frequencies of a predictor. So we see here, if I use a fully connected linear network, so again, just parameterizing a linear network, then I get some predictor. This is in the top that kind of is pretty messy. But once I use a convolutional network, I'm biasing myself towards frequency sparsity in the frequency domain. And the deeper I am, the stronger the sparsity is. So I get a LP penalty where P is 2 over the depth. So with depth 5, I already get pretty extreme sparsity in the frequency domain. And again, this is not coming from constraining the model, because all of these models can represent all linear predictors. It's just coming from the fact that I'm controlling the geometry of the optimization by choosing this specific parameterization. Okay, so far we saw just linear models as either all matrices, and the second example, when I said all functions, I actually meant just all linear functions, all linear predictors. Our next example, we will actually look at all functions. Okay, so we're gonna look now what happens when we're gonna talk about infinite width, one hidden layer ReLU networks. So with infinite width and ReLU activations, I can essentially represent all functions. I can at least, depending what I mean, with appropriate meaning of represent in all functions. Okay? So now I really am optimizing, and I'm going to train this network, and now I'm really optimizing over all functions. But if I actually train it, then the question is which function will I actually converge to that fits the data out of the space of all possible functions? Okay? And the answer in this case, at least for univariate functions, there's a very simple answer here. And we could show that the function I'm getting is the function that minimizes this inductive bias, which is just the integral of the absolute value of the second derivative of the function. So some sort of second order total variation. Okay? Now this is a very natural smoothness penalty. Like if you just came to me and said, okay, I want to optimize over all functions and I want to put some penalty on the functions to make them reasonable, then this would be a reasonable penalty to put. I mean, it constrains the smoothness. But notice that we didn't actually explicitly put it. All we said is, oh, we're going to use a ReLU network, okay? And by the choice of this parameterization, induced, without us even being aware of that, this very natural penalty. Okay. We can also extend this to higher dimensions. This is very recent work. The extension to higher dimension has the same flavor. It gets it technically a bit messier. We have to look now, instead of derivative of function itself, we have to take derivatives of the Redon transform the function. But again, it's something we can characterize, we can reason about, we can say, what are you actually doing when you're training an infinite width one hidden layer network? Okay, so what does all this tell us? How am I doing? Okay, I'm doing great on time. Okay. So what does this all tell us? Well, so for one thing, it has answer Quora questions. There's an actual question from Quora that asks, instead of reading the question, what it basically asks is, I'm going to take my network, I'm going to just add a layer, but the layer is just a linear layer. It doesn't change my model class. How can this have any effect? Okay. And now we know how does this have any effect, because maybe it doesn't change the model class, but it changes the parameterization. Okay. And so note when I say the model class is not important, this is not to say that the architecture is not important. The architecture is very important, but what I would claim is the architecture is not important in the sense that it determines which functions I can represent and which not. It's not that it determines my model class. And so talking in terms of the expressive ability of the architecture is a bit misleading. Rather, the way the architecture is important is because it determines its parameterizations, and it determines the geometry of the search I'm actually doing that induces the inductive bias. Okay? So what we said is that, and again, what I'm dependent on is then two things, both the geometry inside the parameter space, which is one thing that we have a series of papers understanding, and the second is what happens in the function space. How does this bias actually look in function space, which is really what we care about, like things like this integral of the absolute value of the second derivative, or the nuclear norm, all kinds of very rich biases. And I should also say that when I talk about the geometry of the local search, it's even a bit more complex than that, because we use a particular optimization algorithm, and the parameters of the optimization, the hyperparameters of optimization, also have a huge effect. Okay? So things like the batch size or step size have a very, very strong effect, and in particular I want to point out the initialization. So all the results I showed you rely in one way or another on having very small initialization, infinitesimal initialization. In this, we have some recent work that shows how this is really crucial. And the scale of initialization can have a huge effect on the inductive bias. So usually we think of the initialization as controlling, is it good initialization or not, in the sense of do we find a good, is the optimization going to succeed in finding global minima? And what we're seeing here is that changing the scale of the initialization also has a huge effect that we can exactly quantify in some specific models in terms of this inductive bias that we get in the function space. And I'm sure other parameters also have an effect. The batch size, the step size probably has also a very, very strong effect. And again, I would argue we should, when we're doing this now, studying all these in terms of how do they change our inductive bias. Okay, let me end here and take some questions. These are just some, so this talk is based on a bunch of papers. This is maybe about half the papers it's based on. So if you want more details, I encourage you to look at these papers. Okay.
Hey, so the common wisdom actually tend to prefer, for example, Adam over stochastic gradient descent, which is kind of the opposite of what you alluded to. So can you refer to the reason why is that?
You're asking why do people prefer Adam over SGD?
Yes, I mean, there works better.
Okay,
it's not just
so yeah, we definitely, this is work with, I should say, with the Ben Recht and the students in Berkeley. We definitely challenge that. So first of all, Adam in some cases does work better. Okay? What we presented are cases where it doesn't. But usually the reason Adam works better is because, as we saw, Adam is faster. So it does optimize faster. Okay, in some cases, at least. Okay, maybe that even in some cases, but at least what we saw here, it was faster. And so I think that is, if you're asking why people prefer it, I mean, definitely that's a reason, one reason to prefer it. And now, but what we saw here is you should be careful with that, because even if in cases where it is faster, it might be giving you worse inductive bias and worse generalization performance. So I think what you should take from here is not so much that you shouldn't use Adam, although we do make their arguments for why Adam. I mean, Adam was designed for a very particular situation in text where you have very, very sparse features. This is not what's going on in deep learning, and there are many maybe the reasons that we do talk about there about why not to use Adam in various deep learning situations. But what I want you to take from here is not use SGD, don't use Adam, but rather when you choose an optimization algorithm, think not just in terms of how fast it optimizes, but also how good generalization does give you, how does it affect the inductive bias that your model has.
Hi. Given an architecture, is there a way to a priori guess what will be the inductive bias?
Guess or analyze? So there are many ways of guessing, right? I mean, your guesses might be wrong or not. So I think this is what we're trying to figure out now, and we're trying to uncover some principles for that. And I don't think we yet have, and I definitely don't have an answer in the sense that you bring me an architecture and I'll immediately tell you what the inductive bias is, but work like the work Nadav described, looking at the dynamics. We have developed several generic techniques for studying dynamics, analyzing where dynamics go to. We definitely have a lot of directions, I would say. So I hope in several years to be able to answer your question more positively.
Hi. So you mentioned that the optimizer is doing some kind of implicit regularization, but what happens if you combine it with explicit regularization, if you just add the norm to the...
That's a very good question. So for convex models, once you add explicit regularization, then the optimization algorithm doesn't matter at all. So even in convex models, we can see situations, you can look at situations where they're over-parameterized, and then you would rely on implicit regularization. But once you add explicit regularization, then typically there's a unique minima, and once there's a unique minima, then the optimization algorithm doesn't matter. I would argue, and this is getting very speculative, and I don't have a lot of basis for this, that in highly non-convex models and in deep learning, even if you have an explicit regularizer, then still, because the problem is very sort of non-convex and you're going to, there's still multiple minima even with the regularizer, then the implicit regularization still has a very large effect. And I would argue still has the greater effect than the explicit regularization, at least in the cases we look at it. And as evidence, look at forms of explicit regularization like dropout or weight decay. So what we're seeing is that if you didn't have any type of complexity control, not from the optimization and not from them, you would get trivial, you get 0 accuracy or 10% accuracy, you get trivial results. If we train the models without things like dropout or weight decay, you already get very good accuracy. Once you add these things, the accuracy improves, but still improves. You get down from get up from like 10% accuracy to 80% or 85% accuracy. Add dropout and all those things, you get from 85 to 87 or 89, depending on your problem. And so this leads me to believe that still the main force in play is still the bias induced by the algorithm, and the explicit regularization is just supplemental. But as I said at the beginning, I mean, what I said now is not based on fact or on math. Okay, it's just a speculation.